Welcome back again to the G proof, our rigorous mathematical proof that God exists using first-order predicate logic and 5 axioms that no scientist can reasonably deny. This is video 6 out of our 9 videos, undefined terms, definitions, and the first 3 axioms. We have a website at thegproof.org. I'm Mark Lawrence Donald Emerson, and I'm your teacher. And this work is based on the work of many other people, as I've told you before. Here's a map of all 9 of the videos. You can see we've done a lot. We've got a lot of cyan color on there. We've been there, done all that. And right now we're up here all the way to video 6. In video 6, 7, and 8, I'm going to present the proof. In this one, we're going to do the undefined terms, definitions, and the first 3 axioms. And then the last 2 axioms, consistency and an informal proof in video 7, and our formal rigorous proof in video 8. So after all that's done, then in video 9, we'll talk about the consequences of the proof. Okay, so here we are in video 6, and so here's an outline of video 6. I'll just go over the main points, the main bullets. We're going to do a quick review of videos 1 through 5. We're going to talk about the 3 undefined terms. We're going to talk about 2 interpretations of what we call absolute phenomena. We're going to cover our first 3 definitions, and then our first 3 axioms and their justification. Okay, quick review of videos 1 through 5. Here we are in the outline. So, inputs and outputs of a mathematical theory. I taught you this in video 1. What is formal mathematics? It's a system for knowing purely abstract things with absolute certainty. How do we do that? We do that by creating a formal mathematical theory with 3 inputs and 3 outputs. The inputs are a logic system, undefined terms, and axioms. And the outputs, the 3 outputs, are defined terms and their definitions, theorems and their proofs, and a calculation system, which we don't need. So what we've done here is we've created a formal mathematical theory of phenomena and causation. And it has 3 inputs and 2 outputs, since we don't need the calculation system. Let's look quickly again where those things appear on our map, our diagram. The logic system was, I taught you that over here in videos 3, 4, and 5, and you need to know that to move forward with what we're going to do now. Our 3 undefined terms are here in this video. We're going to do that today on this one. Our 3 definitions are right here, also in this video. The 5 axioms are split between this video and the next video, video 7, and our 3 theorems are down here in video 8. All right, now, when we're creating a mathematical theory, we get to play with the axioms and see what happens. And so with if you change the axioms around, or you take a different set of axioms, you get different results. And so this playing around and seeing, okay, if I try this axiom or this axiom, we adjust this one, or we get rid of that one, we put this one in, we can, by doing that and seeing what the possible results are that can be proven, we are exploring a mathematical space of ideas. Very fascinating stuff. My son Jonathan and I did a lot of playing around with the axioms before creating these videos. And we're presenting one particular set of 5 axioms, which we're calling version 1 of G theory in these videos. Now this version 1 is a valid proof that God exists. And then we have, the theory is evolving though, and we've also created version 2, which is more advanced. And the result is more interesting, it's more powerful, it reveals more about God than is revealed in version 1. So we made a decision to present version 1 in the videos because it's simpler. And we needed to teach, I knew I needed to teach all of the logic, and so version 1 is a good starting point. It does prove that God exists, and then version 2 moves forward from there and to a deeper understanding. And what happens in version 2 is we revise the axioms. We make some changes in the axioms, and the results are different and more powerful. And you can read about that in the technical papers, but I recommend that you watch all of version 1 first, so you have that as a starting point. And one of the fascinating things about this exploration and playing with the axioms is it appears that whatever we do, however we adjust them, that God or something like God seems to inhabit this space, even as we play around with it, and God just appears in a slightly different form this way and that way. It's very interesting. Now, in these videos, in version 1, what we're going to get ultimately in theorem T3 is we're going to prove this right here. Now, you already know about the backwards Z with the exclamation point means there exists exactly one. There exists exactly one G such that capital SG, and capital OG. those are definitions we're going to cover in this video. This means there exists a unique phenomenon that is self-caused and omnipotent. And here's a diagram of it. This diagram shows God, obviously, in this big pink ellipse, and it shows this loop. It's coming back on itself. It means it's creating itself. And then all this blue and the green circles down here, these are other phenomena, and some of them are causing others of them, but you see God is causing everything, because there's an arrow going from God to every circle. Okay. So now, first order predicate logic, which I taught you in videos 3, 4, and 5. Quick review of what we did there. First order predicate logic provides a rich syntax or grammar for terms and for sentences. Terms are things, sentences are either true or false. It provides a rigorous mechanical procedure for constructing proofs and for checking the correctness of proofs. And it guarantees the truth of any sentence that has a correct proof. So here's what we learned. We learned about how to form sentences with predicates and variables, like these here. And we learned how to form larger sentences using logic systems, symbols like these right here. And we learned a bunch of logic rules, proof starting rules, inference rules, and proof ending rules, all these, a bunch of inference rules. We've covered all that in videos 3, 4, and 5. And we learned how proofs are constructed in videos 3, 4, and 5. All right, so now, let's dive in here to our 3 undefined terms. 3 undefined terms. Here we are in our outline. So I'm going to look at them, give a quick overview, and then go into each one. So what's a phenomenon? There are 3 undefined terms. The first one is phenomenon, and that's anything that exists or happens. And every variable in our theory, like A, B, C, the lowercase letters, X, Y, Z, R, S, T, they each represent a phenomenon. The second undefined term is a part of. This is a predicate with 2 blanks. And so we have this symbol, which is a square with the right-hand side missing. The blank on both sides, it means there's a phenomenon in each blank. This phenomenon is a part of that phenomenon. And our third undefined term is causes. This is also a predicate with 2 blanks. We use this triangle that's filled in and points to the right. And this means, with the 2 blanks, a phenomenon in each blank, the first phenomenon causes the second phenomenon. Okay, now let's dive in and look real closely at what phenomenon. This is very important. We're going to spend a little bit of time on this now, exploring what phenomenon means. Phenomenon are nouns. Okay. A phenomenon, like I said, is anything that exists or happens. Some quick little examples. Here, the number 88 is a phenomenon. The sun, humanity is a phenomenon. Politics is a phenomenon. Newton's 3 laws of motion, that's a phenomenon. Chemistry. Fun is a phenomenon. Belief in God is a phenomenon. Also, atheism is a phenomenon. Now remember that the value of every variable in our theory is a phenomenon. So little x represents a phenomenon. Little r represents a phenomenon. And phenomena can be classified in a multitude of different ways. Let's look at some of these. We can classify them by single versus collection. Okay, a single thing or a collection of things. For instance, the number 23, that's a single phenomenon. All the odd numbers, that's a collection of things, including 23. And the odd numbers are a phenomenon. Okay, how about this? The pinky on my right hand, right here, and my right hand, including the pinky. So my right hand is a collection of things that includes my pinky. Okay, one of the protons in a particular iron atom. Okay, iron is an element, and every iron atom has 26 protons. So if I look, here's one atom right here, one atom of iron, and it has 26 protons in there. And now let's look in there and it's like that proton. That one right there, that proton right there, that's a phenomenon. Okay, it's a single thing. How about, but it's a look at this. All the protons, all 26 protons in that iron atom, that's a collection of things. All right. One of the things that Jack loves about Jill, that's a phenomenon. And how about this? Jill's long hair, her pretty smile, and the funny way she tumbled down the hill, all of which Jack loves about her. That's a phenomenon. It's a collection of things, of which this is one. Faraday's law of induction. This is a law of physics. very interesting. I'm not going to explain it. It's one law. Maxwell's 4 laws of electromagnetism. This is 4 laws, but this is one of them. So this is a collection. This is a single thing. A particular kernel of corn. The corn that I ate for dinner last night. That's a collection. All right. Another way we can classify phenomena is by time. A phenomenon could be in the past, like the American Revolution. It could be in the present, like how you are feeling right now. That's a phenomenon. The current state of your computer's memory. That's a phenomenon in the present. Or in the future. The next lunar eclipse, that's a future phenomenon. Or any combination of these things. How you have been feeling all day today, including right now. The entire history of the planet Earth. That's a collection of things, past and present, and maybe future too. Well, it's not history if it's the future. All right. Or it could be beyond time. The multiplication table. When is that? It's beyond time. Quantum mechanics. Beauty. Beauty is timeless. The real numbers. When are they real numbers? They just are. But time itself is beyond time. All right, we can classify phenomena by place. Where are they? Okay, phenomena could be somewhere, like the city of Los Angeles, California, the North Pole, Jupiter's giant red spot. I've never been there. I don't think you have either. Okay, or it could be in multiple places. The branch offices of Bank of America, well, they're all over the place. French citizens, well, probably most of them are in France, but there are a lot of them in other places besides France. Or moving from place to place. The cars driving on Interstate 90, well, there's a whole bunch of them, and they're all moving. The waves in the Pacific Ocean, that's a phenomenon, and they're moving from place to place. Or it could be everywhere. The second law of thermodynamics, that's everywhere. Space is everywhere. Or nowhere. The empty set, where's that? The number 9. And I don't mean the numeral 9, the number 9. That's nowhere. Okay, we could classify phenomenon by degree of abstraction. It could be a very concrete phenomenon, or it could be abstract or even more abstract. Let's look at some examples of this. The potato that Lorraine ate yesterday, very concrete. Potatoes as an agricultural commodity, well, that's abstract. How about feeding the world? That's even more abstract. How about this one? A particular car crash. That's pretty concrete. The risk of automobile accidents. Well, that's more abstract. Danger. That's even more abstract. A particular computer program written in the Pascal language. Okay, maybe it's an accounting program and it does this and this. Okay? How about a Pascal compiler that outputs executable programs? Well, maybe you don't know what a compiler is. If you're a software engineer or a programmer, you do. That's more abstract. How about a meta-compiler that outputs a compiler? That's even more abstract. I wrote one of those once. Okay. The fact that 4 plus 8 is equal to 8 plus 4. That's very concrete. How about the commutative axiom of addition for the integers? A plus B equals B plus A. That's more abstract. How about the theory of abelian groups? So this is kind of from higher mathematics, abstract algebra, and that's even more abstract of the same idea. All right, we can classify a phenomenon by state versus process. Okay? A phenomenon can be the state of something at a particular point in time, or it can be the process by which something changes from this state to another state at another point in time. Or it could be a collection of states and processes over a period of time. Let's look at 2 examples. How about we have a signal, a traffic signal. We have a signal at an intersection at a particular time when it is green for the north-southbound traffic and red for the east-west traffic. Or another state of that signal is 2 minutes later when the red and the green are switched the other way. Okay, these are states. How about this? The change of the signal, including passing through the yellow light. That's a process of going from one state to another state. How about this? the signal during the year 2012, well, thousands of times, I don't know how many times, the signal would have changed and gone through different states and different processes, again and again. Here's another example. The state of Joseph's physical body when he was suffering from a cough. And then here's another state, Joseph's body after he recovered. Okay, now here's a process. The process by which Joseph's cough was healed. His body went through some things and moved it from one state of ill health to a state of health. And here's a collection of things, Joseph's body from age 20 to 30. A bunch of states, a bunch of processes all mixed together. That's also phenomena. We can classify phenomena by type versus instance. So a phenomenon could be a general type of thing, or it could be a particular instance of that type. We'll look at several examples. A 2012 Honda Accord EXL. That's a type of car, right? Mine, actually have one of those. My 2012 Honda EXL Accord is red. Okay, that's a particular instance of one. How about this one? A computer operating system. That's a kind of thing. Linux. That's a particular instance, a particular kind of operating system. How about The Grapes of Wrath by John Steinbeck? Well, okay, that's a book that John Steinbeck wrote, but it got printed in millions of copies. It was a bestseller. And one of the instances was a copy that Susan had. Susan has a copy of The Grapes of Wrath. Her copy. That's a particular instance. All right, a question. That's a kind of thing. How about this? Why is the sky blue on a clear day? That's a particular instance of a question. It's also phenomena. These are all phenomena. The office of the President of the United States, POTUS. That's a kind of thing. Thomas Jefferson in 1803. Well, he was president in 1803. That's an instance of someone in that office. Travel by sea. That's a kind of thing. How about this? Magellan's voyage across the Pacific Ocean. That's a particular instance, very famous, monumentally significant instance of travel by sea. Mendelssohn's Violin Concerto. That's a kind of thing. How about Joshua Bell's first public performance of the Mendelssohn Violin Concerto? That's a particular instance of that thing. So now, let's look at just a few more example phenomena, just so you have I want you to understand what we mean when we say phenomena. Everything that happened in the year 2001, that's a phenomenon. Everything reported in the news on this day, today. Everything that happened, or that will happen in the year 3001. Mankind's struggle for liberty. George Washington's victory against British tyranny. The tragedy that the United States today incarcerates more people. We have more people in jail and prison in the United States today than voted for George Washington in the first presidential election. I think that's a tragedy. In any event, it's a phenomenon. The question of whether George Washington has turned in his tomb. Interesting question. Fear of government. The falling of apples from a tree. That's a phenomenon. Gravity is a phenomenon. All the colors that your computer monitor can display. The Schrödinger equation. That's a central equation in physics and quantum mechanics. Vegetarianism. Logical identity, which is what we mean by the equal sign. That's a phenomenon. And still more examples. The life of Mary Magdalene. That's a phenomenon. The life of Albert Einstein is a phenomenon. Space, with its relativistic curves and distortions. That comes from the general theory of relativity by Einstein. Time, including its relativistic expansions and contractions, also from the theory of relativity. Timelessness, whatever that is. Matter, in other words, anything having mass. Energy and its mass equivalent, that's what E equals mc squared about, also from Einstein. Charles Darwin's notes from his voyage on the ship Beagle. The book of Genesis in the Holy Bible, that's a phenomenon. The evolution of bacteria resistant to an antibiotic, that's a phenomenon. DNA. Love is a phenomenon. The entire universe, past, present, and future. That's a phenomenon. This video is a phenomenon. Your experience of watching this video is also a phenomenon. All right, now, when we speak of phenomenon as our undefined term, the phenomena we're talking about have to be unambiguous. Now, something is ambiguous when it has more than one possible meaning and it's not clear which meaning is intended. So, our theory does not tolerate vagueness or ambiguity. In our theory, each phenomenon must have a precise meaning. However, we might speak vaguely or ambiguously about various phenomena just for the purpose of giving examples. It's pretty hard to get something extremely specific. For instance, we use the word chemistry. One of the things I mentioned back there was chemistry. Chemistry is a phenomenon. I use it as an example, but it was ambiguous. I mean, what precisely do we mean by chemistry? Here's some possibilities. Chemistry as understood in the year 1850. Inorganic chemistry. The chemistry of the rare earth metals as it's understood today. All of chemistry known and unknown. So this is an example of what we might mean when we say chemistry. There are many other possibilities too. So, but each of these examples is a distinct and separate phenomenon. So even though I say chemistry, it could be a million different exact phenomenon that might mean. So the important thing to understand is that when we say our phenomenon is an undefined term in our theory, and this variable x represents a phenomenon, we mean a precise phenomenon, not an ambiguous one. Also, relationships have to be unambiguous. A pair of phenomenon, if we have a phenomenon here and another phenomenon there, whatever these two phenomena, I got one in each hand, they're related in two ways. They're related via a part of relationships and causes relationships. And these relationships have to be unambiguous. So here we go, once again. I've got a phenomenon x and y. Here's x in this hand and y in this hand. Okay, x is a part of y. Now, that has to be either true or false. Either this is a part of that one or it's not. Not maybe. Maybe's not okay. Is this a part of that? Well, maybe not. No, it's not okay. The relationship has to be precise. It either is or it isn't. It either is the part of a relationship between these two phenomena, these two precise phenomena, is either true or it's false. Same thing for the causes relationship. Does this one cause that one? Either yes or no. This causes that is either true or it's false. Not sort of. Does this cause it? Well, sort of. No, that's not acceptable. Okay? So the nature of our undefined terms of phenomenon and of the relationships is that they are exact. Now, for a given phenomenon x, let's say I have here x is in this hand, each of the following questions has to have unambiguous answer. What is x a part of? Okay, there are other phenomena. This is, there needs to be a definite answer. We probably don't know the answer. We might not know the answer, but an answer exists. This is what our theory says. So this is a part of this or whatever. Okay? What is a part of x? What things are inside of x? And the other way around, what is x inside of? These things have unambiguous answers. Also, what causes x and what does x cause? These things exist in a precise way. Okay, what I'm trying to convey here is that our theory is not based on vague things. It's not based on sort of things and maybe things. It's based on exact phenomenon with exact relationships between them. So based on precisely what we mean by chemistry, its part of relationships with other phenomena will differ. If we mean this kind of this meaning of chemistry, then its part of relationship be different than if we have some other meaning of chemistry. Also, same for its causes relationship. This meaning of chemistry might cause some things or be caused by something. And if a different meaning of chemistry, those causation relationships would be different. All right, so that takes care of our exploration of our first undefined term, phenomenon. So I made that cyan. So now let's move on to the next one, which is the is a part of relationship. So here we are in our outline. It's a part of predicate. It's a predicate, remember? So like I said, the symbol is the square with the right-hand side missing. So we can say X is a part of Y. Phenomenon X is a part of phenomenon Y, putting X and Y into the two blanks. And what that means is that X is inside of Y. This is, diagram shows it symbolically. Okay, the phenomenon X is inside of, it's a part of the phenomenon Y. Now here's some examples. I already talked about this. The pinky on my right hand is a part of my right hand. Antarctica is a part of the planet Earth. A processor chip is a part of a computer. A computer cannot function without a processor. An oxygen atom is a part of a water molecule. A water molecule is H2O. It has 2 hydrogen atoms and 1 oxygen atom. That oxygen atom is a part of that water molecule. DNA, this long, complicated spiral molecule, helical molecule, DNA is a part of all known living systems. And no living system has ever been found yet that has no DNA in it, as far as I know. I'm not a biologist. Picasso is a part of great artists. Writing is a part of human activities. Romeo and Juliet is a part of Shakespearean plays. Okay? Now, when we say part of, we mean necessary part. In our theory, is a part of means part in the strong sense of a necessary part. In other words, like this. The number 5 is a part of the odd integers. If you remove the number 5 from the odd integers, you don't have the odd integers anymore. If you take the odd integers without 5, it's not the odd integers, it's something else. It's not the odd integers, though. How about an engine? An engine is a part of a drivable car. Well, if you take out the engine, I don't think the car is going to drive. Now, supposing we have some phenomena, we'll call it S, and it has 3 parts, T, U, and V. Now, here it is, the diagram. You can see the yellow circle, the big one, that's S. I've labeled that one S. And then T, U, and V, the pink ones, the small circles, they are each parts of S. So we have these 3 relationships here. We have T is a part of S, and U is a part of S, and V is a part of S, and we can see all 3 of those relationships by looking at the diagram. Now, what does this mean? This means that T, U, and V are each necessary to the very existence of S. Without T is that pink circle there on the upper left. Without T, S would not be S. And without U, S would not be S. And without V, S would not be S. In other words, no donut holes. It means phenomenon S does not exist unless all of its parts also exist. So we have this no donut hole principle. A phenomenon does not exist unless all of its parts exist. Otherwise, there would be donut holes. Here I made S this magenta color, and I've got these white circles, and it's like they're empty. It's like there's S with holes where its parts would be. Well, it's not S if it has those holes in it. It has to be complete to be S. The donut holes leave S incomplete, which means it doesn't exist. In other words, S as a phenomenon doesn't exist if these parts of S don't exist. It's like a drivable car. Oh, here's my car. It's a drivable car. It doesn't have an engine. The engine's not there, but it's drivable. Oh, yeah, right. Okay. Some more examples of is a part of. 13 protons is a part of an aluminum atom. Every atom of aluminum, that's what makes it aluminum, it has 13 protons. It's an element. An aluminum nucleus is a part of an aluminum atom. So an aluminum nucleus has 13 protons and usually 13 neutrons. And then that's the nucleus. And then at some enormous distance, about 100,000 times further away, are electrons that are doing something. They're going around or they're making wave functions, doing bizarre things. There are 13 electrons out there. That's the aluminum atom. So the nucleus is a part of the whole atom. The Earth is a part of the solar system. A steering wheel is a part of a car. The Origin of the Species, that's a book by Darwin, Charles Darwin, is a part of all books written before the year 2000. There are a lot of books that were written before the year 2000, millions of them. And this is one of them, The Origin of the Species. The Holy Bible is also one of those books. The Holy Bible is also a book that was written before 2000. Also, you might not have heard of this one, Principia Mathematics. Principia Mathematica by Russell and Whitehead. Russell and Whitehead are two of the people named on the second slide of each of these videos that develops the mathematics that we're using in these videos. That book is a part of all books that were written by before 2000. It transformed mathematics, that book. The Bhagavad Gita from India, from ancient India. This is a book that's part of all books written before 2000. The fundamental theorem of calculus, profound theorem, is a part of mathematics. Okay, so now that takes care of our exploration of the is a part of undefined term. Now I made that one science, and now let's go on and take a look at the causes predicate. All right, here we are in our outline, the causes predicate. This is our last of the three undefined terms. So we have a special symbol for causes, which is this solid filled-in triangle that points to the right. And so if I say R causes S, where R and S are both phenomena, it means that phenomenon R causes phenomenon S. And we draw it this way. We say here's R and here's S, and we put an arrow. And the arrow means that this one causes that one, okay? Now I'm going to give you some loose examples, and I'm going to explain why I use the word loose in a few minutes. These are loose examples. Gravity causes apples to fall from a tree. Writing causes books. See, the reason they're loose is because it's not really quite that way. I'm just trying to give you an idea, and then we'll talk about what we really mean by causing in a minute. An iceberg caused the sinking of the Titanic. Printing fiat money causes inflation. Vitamin C deficiency causes scurvy. Scurvy is a disease. The union of an egg and a sperm causes pregnancy. The oscillation of the electrons in a wire causes radio transmission. That's what an antenna is. Government corruption causes injustice. All right, now, let's get less loose. Let's tighten up what we mean by causation now. And that is, it has to be a sufficient cause. And we're going to give an example of the apples coming off of the tree. In our theory, cause means sufficient cause. What causes the apples to fall from a tree? Well, gravity alone is not enough to explain why apples fall off of a tree. Now, here's another phenomenon we're going to call little c that might be a sufficient explanation. Now, look at this c. It's this great big circle, lowercase letter. I said little meaning the lowercase letter. This big yellow circle here is a phenomenon. It has 4 parts in there, which are pink. The one at the top is Newton's laws. Newton's laws of gravitation and motion. He has 3 laws of motion and 1 law of gravity, so that's 4 laws. 4 laws there in that pink one. The mass of the earth is very massive. The masses of the apples, because the law of gravity depends on the mass of the earth and the mass of the object, and how far apart they are. And the breaking of the apple, the apple's not going to fall off the tree until its stem breaks. It'll hang on the tree for a long time, and then at some point, for some reason, the stem breaks. Okay, and then it falls. All of those things together in this big yellow circle. Perhaps, I'm not sure, but I think we're getting close. That phenomenon, that whole thing as a phenomenon, that is what causes the falling of the apples from the tree, which I'm calling little f. Okay, so you got N and E and A and B for these ones in the pink ones. Now let's look at what we have here, our relationships, okay? We have N is a part of C. That's Newton's law of gravity. That's part of this C, this big phenomenon. Also, E is a part of C, the mass of the earth. The A is a part of C, the masses of the apples. And B is a part of C, the breaking of the apple stems. And then what do we have down here? We have C causes F, okay? So the C causes F. We're using the causes predicate. Okay? So the entire phenomenon C of all with these pieces, with these parts, that is what causes F, the falling of the apples from the tree. Okay. Here's another example. Books. What is a sufficient cause for books to exist? What causes books to exist? Writing alone is not sufficient. here's a phenomenon that might be sufficient. I've got another big yellow circle. I didn't put letters on them, little letters. But let's just to get an idea here. Okay, maybe this big thing causes books. Okay, and its pieces are, the parts of it are the author's concept, motivation, and skill, the writing process, editing process, the printing process, the binding process. And if you put all that together, that is what causes books to exist. I don't know, but this is to give you an idea what we mean by sufficient cause. Why questions? Causation answers the question why. When we ask why something exists, we want to know what caused it. Why did she get pregnant? Because she had sex with her boyfriend. Having sex caused her to get pregnant. See? So suppose A causes B. We ask, why B? And the answer is, because of A. You see? In fact, we often answer why questions very often by starting with the word because. The word because reverses the cause predicate. Let me show you. Because. It be the cause that. Now watch what happens here. Putting the same question out. Having sex, okay, here's the sex, caused her to get pregnant. So the sex caused the pregnancy. Having sex caused her to get pregnancy. Now watch what happens when we use the because. It turns it around. She got pregnant because she had sex. See? It turns it around. Because turns the cause predicate around. All right? And we're speaking loosely here about pregnancy causing sex. There could be other factors too. All right. Let's look at some more why questions. Some more examples. Why do apples fall from a tree? Because gravity pulls them down. Well, that's loosely speaking. We actually looked at that more carefully. Why are there books? Well, because people write them. Again, that's loosely speaking. Why is there injustice? Because the government is corrupt. Loosely speaking again. So, all right. Now, there are lots of why questions for which we do not have answers. Why does the Earth have only one moon? I have no idea. I don't think anyone knows. Why did Beethoven go deaf? I don't think anyone knows that either. They even dug him up from his grave long after he died to see if they could figure it out. One of the fundamental quests of science is to answer the question why. Now let's talk about time. Traditionally, causation is based on time. The cause happens before the effect. So if this causes that, this has to happen before that happens, right? The fact that the student learned the material for the class caused her to get an A in the class. Well, her learning happened before she got the A. She didn't learn it after she got the A. She didn't get the A first and then learn it. The fact that the seeds were sown in the ground caused the crops to grow. In other words, the sowing of the seeds in the ground happened before the crops grew. You know, the crops don't grow and then you plant the seeds. Well, I mean, plant them for the next crop. But this crop here, you don't plant its seeds after the crop has grown up, because the causation is based on time. The cause happens before the effect. But what causes time? Time's a phenomenon. Why does time exist? This question makes no sense if causation is required to be based on time. You see? And we are taking a broader view of causation that goes beyond time. Our causation is entirely abstract, and it includes traditional time-based causations. This is part of it, but it's not the whole story. All right, so now, let's move on in our outline here. We're going to talk about two interpretations of something we're going to call absolute phenomena. We're going to distinguish relative phenomenon from absolute phenomenon. So a phenomenon is either relative or absolute. Now what do I mean by that? I'll show you. A relative phenomenon is caused by a different phenomenon. See, now look at this here. I've got an orange circle here and a yellow circle here. They are different. They're not equal. This one causes that one. So this one over here, the yellow one, is a relative phenomenon because it was caused by something else, something different, something not equal to it. An absolute phenomenon is not caused by a different phenomenon. It's not like this. And there are two possibilities. Either it's self-caused. So here I have this yellow phenomenon. What causes it? Well, it causes itself. And the other possibility is it's not caused by anything at all. There it is. It's no cause. It just exists. It has no cause. So an absolute phenomenon is either self-caused or not caused at all. And a relative phenomenon is caused by a different phenomenon. See that? Now let's look at relative phenomenon for a minute. So like I said, a phenomenon S is a relative phenomenon if and only if it is caused by a different phenomenon R. So here we have, okay, here's the diagram that I just showed you. Look at the orange and the yellow. Now I put R and S in them. So R causes S, and very importantly, R does not equal S. That makes S a relative phenomenon. Don't know about R, but S is a relative phenomenon based on this. And that means all of the following. S exists by virtue of R existing. R must exist before S exists either in time, if we're dealing with time-based causation, or in logic, or both. R contains everything that's needed to create S. R creates S either directly or indirectly by creating an intermediary that creates S. Does that make sense? So the existence of S is relative to the existence of R. That's what we call it a relative phenomenon, okay? It's relative to R, which is something else. Now let's look at absolute phenomenon. Now it might be difficult to imagine an absolute phenomenon, but supposing that the phenomenon R either causes itself, which shows this loop around, or it's just caused, it has no cause. Okay, it's either self-caused or it's not caused at all. It just exists. Now, in my opinion, this would mean that R is eternal. It has always existed and will always exist. Because if it's not eternal, then at some point it came into existence, and it's hard to imagine that it would have just popped into existence without something causing it at that time to become, for it to just appear without any kind of cause. That's hard for me to imagine. So I think that absolute phenomenon are eternal, and that means outside or beyond time, outside of time. And here's some possible examples of absolute phenomena. How about the concept of identity? A is equal to A. Well, what caused that? And when did it happen? It just is. It just is. Now, did it cause itself, or does it just exist without a cause? I don't know, but I think it is not caused. I don't think there's anything else that caused that to be. Logical tautology, we'll talk a little more about what a tautology is in a few minutes. But a tautology is a statement in logic that you can prove with no givens. How about this one? This is very easy to prove. It doesn't matter what sentence Q is. Q could be any sentence. It could be true sentence or false sentence, but Q implies Q will be true. That makes it a tautology. It's true no matter what. How about, is that an absolute phenomenon? I think that might be an absolute phenomenon. I don't think that anything causes that to be true. How about energy, including its mass equivalent by E equals mc squared? Now, some physicists and astronomers think that perhaps the total amount of energy, including mass, in the universe stays the same all the time. Maybe that's true, maybe it's not, but if it is true, if it's always that much energy in the universe, is the energy in the universe an absolute phenomenon? I don't know. How about absolute truth? Well, what do I mean by that? Let me show you what I mean by that. Absolute truth, this is an interesting one. Does absolute truth exist? Well, consider the following statement, which we'll call P. Okay, here's P. Quote, some absolute truth exists. Unquote. I put it in red. Now, if this sentence P is true, then, well, an absolute truth clearly exists, because what does it say? It says some absolute truth exists. Well, if that's true, then an absolute truth exists, right? Okay? But what if P is false? What if this sentence, this red sentence here, is false? Well, that means that not P is true. It means no absolute truth exists, right? If some absolute truth exists is false, that means there is none. No absolute truth exists. Now, if no absolute truth exists, isn't that an absolute truth? In other words, if true that no absolute truth exists, then isn't that statement an absolute truth? And if that is an absolute truth, if it's true that there's no absolute truth, then doesn't that contradict P? That makes P true. If P's false, then it's true. But if it's true, there's no problem. P can be true, no problem, but if it's false, then it's true. So, is an absolute truth an absolute phenomenon? In other words, this idea, is this eternal? I think so, in my opinion. What do you think? All right. Now let's talk about self-caused phenomenon versus uncaused phenomenon. In other words, an absolute phenomenon, as we have defined it, an absolute phenomenon either causes itself to exist, it's self-caused, or it just exists without a cause, one or the other. Now, is it possible to distinguish whether an absolute phenomenon is self-caused or uncaused? In other words, something like P implies P, or something like the identity. Is it possible to tell? Is it self-caused or is it uncaused? Now, in my opinion, probably not. In my opinion, also, it doesn't really matter. In my opinion, also, I have many opinions, it's absurd to entertain the idea that both exist at the same time. In other words, is it possible for a phenomenon to be self-causing and also just exist without a cause? I think that makes no sense at all. I think that it is fair to either take one frame of view or the other. In other words, we look at these phenomena as absolute phenomena. We can either say, okay, they are self-caused, or we can say they're uncaused. We can look at it one way or the other. And I think that the distinction is basically an aesthetic choice, and I'm going to invite you to just take your pick. Now, by choosing one way or the other, but not both, and by making some reasonable adjustments to our axioms, we can prove essentially the same result either way. One way we get that God causes itself to exist, and the other way we get that God just exists without a cause. Okay? Now, we have different versions of G theory, as I've explained to you. In version 1, which is what we're doing in these videos, we interpret absolute phenomenon as self-caused. We make the choice that we're going to say, okay, I don't really know which way it is, but we're going to interpret it as being self-caused. And now this is a simpler approach. That's why we're doing it in these videos. The mathematics is a little simpler this way. Now, version 2 takes a different approach. As I said, it permits absolute phenomena to be either self-caused or uncaused. And, but version 2 is more advanced. And so after you've digested version 1 and understood it at sort of the first level of understanding God, then move to the next level of understanding God in version 2. You can read about that in the technical papers at thegproof.org. And that's a more sophisticated result. I'll talk about it a little bit in video 9. Nevertheless, version 1's proof here is a valid proof that God exists. Okay, so that takes care of our 3 undefined terms. I've made this box here cyan colored for our undefined terms. Now, what are we going to do with this? We're going to use them. We're going to use them when we make our definitions. And we're also going to use them when we do our axioms. And so now let's move forward to the definitions. Let's look at our first three, defined terms. And so first 3 definitions. Here we are in our outline now. We're going to do our definitions. And the first one is going to be is self-caused. All right, this is a definition. So here is definition number 1, and that's the capital letter S. So we're going to use the capital letter S. S means blank is self-caused. It's a predicate. S is a predicate with one blank, means S is self-caused. So now look what since I can use the capital letter S with one, so that's one blank, I put one small letter after. So here I have SR, capital letter S, lowercase r. This means that R is self-caused. In other words, R causes itself. So SR means this. It means R causes R, right? In other words, R is self-creating, self-causing, self-creating. If you cause something to use this, I think that's the same thing as creating something. Okay? And here is the definition. This is our formal definition, D1, and what it says is, for all R, SR, if and only if R causes R. In other words, R is self-caused. So this means, you see, remember I explained that a biconditional means logical equivalence. If I have P, if and only if Q, it means P and Q are logically equivalent. Well, what does it say in parentheses here? Inside the big parentheses, it says SR, if and only if R causes R. In other words, SR is logically equivalent to R causes R. SR means that. It makes sense for a definition. It's saying, instead of writing R causes R, I can just write SR. But I can do it for A or W, because I can use UI on this universal quantifier here, and whenever I need. In fact, that's what we're going to say here. See, all I need to do is use UI if I need, let's say, A, or I need X to be, I want to do SX. All I have to do is plug it in with UI, and then I get SX is equivalent to X causes X. Not only that, we can use the BC to unwind the biconditional either way. So if I plug in, let's say, W, I know that SW is equivalent to W causes W, but if I want to move one direction, I do UI and then BC on it, and I get SW causes, SW implies W causes W. Or the other way around, like if I put E in, I could get, if E causes E, then SE, because E causes E and SE are equivalent, and so I can do it either way with BC. And we'll do that in our proof. In our proofs, we'll use a definition, and we'll always, whenever we bring a definition in, we'll copy it in with repetition. Then we'll do UI to get the variable that we want in there, and then we'll do BC to get the conditional to go one way or the other, depending on what we need in the proof. Okay. Moving on to definition 2, which is the capital letter C. Capital C is a predicate with one blank. It means blank causes something. So here, capital C, lowercase r. This means R causes something. In other words, there's something out there. I have a phenomenon here. It says, well, this thing causes something. I don't know what it causes, but it causes something. See, now look at this statement right here. It says, there exists an S such that R causes S. In other words, there exists something that R causes. You see, there exists some phenomenon S that R causes. That's what this here says. We're going to use that in our definition. Now, it might be that R causes additional things, something else. That doesn't matter. What CR means is that R causes at least one thing. So here's the definition. For all R, once again, we start with a universal quantifier. CR, if and only if this thing here exists in S such that R causes S. In other words, we have a universal quantifier outside and inside the parentheses a biconditional, which means that in CR, the thing we're defining is on one side of that biconditional. And the biconditional says this thing we're defining is equivalent to whatever this other thing is. So CR is equivalent to this expression here, which is the same as what I wrote up there. And that says there exists something S such that R causes S. R causes something. See that? So again, since we can use UI and BC to unlock it either way, get CW implies there exists an S such that W causes S, or we can do it the other way at plugging E in here. Okay? All right, now our last definition, with the definition 3. We're going to do another definition in the last video. Okay. This is omnipotence. Capital O is a one-place predicate, a predicate with one blank. That means blank is omnipotent. So if I do capital O, lowercase q, what does this mean? It means Q causes everything. Q is omnipotent. Now look at this expression right here, this statement right here. It says, for all t, Q causes T. In other words, for all things, whatever thing, for everything, Q causes it. If Q causes everything, for every phenomenon T, Q causes T. Well, that's what omnipotence is. Q is omnipotent if it causes everything, and that's exactly what this says. So let's use that in our definition. For all Q, always start with the universal quantifier. Then we have OQ, if and only if something. So we're saying that OQ is equivalent to this thing over here, which is what I wrote up there. In other words, OQ, Q is omnipotent, means it's equivalent to, for all T, Q causes T. In other words, for all things, Q causes that thing. In other words, Q causes everything. OQ is equivalent to saying Q causes everything. In other words, Q is omnipotent. All right? And again, because we have the universal quantifier, then we can use this in our proofs. We'll bring it in with repetition. Then we'll do UI to get whatever variable we want on the O. And then we will use BC to get a conditional one way or the other. Okay, that takes care of our definitions 1 to 3. And now let's move on to axioms 1 to 3. Here we go, our first 3 axioms and why they're justified. Here we are in our outline. We'll begin with axiom A1. And here it is. This A1 is the axiom of sufficient reason. It says that every phenomenon has a cause. All right, now let's look what it says here. It says, as I have a universal quantifier out here. It says, for all R, then the next existential quantifier, there exists a V such that V causes R. Okay? In other words, for every phenomenon R, there exists a phenomenon V such that V causes R. What does that mean? That means, okay, supposing I have some particular phenomenon. Since this is a universal quantifier out here, let's say I want to say W, okay? So I put W in with UI, and what do I get? I get there exists some V that causes W. In other words, something causes W. I don't know what the V is. I could do EI on it, which we'll do in proofs. The point is, for anything, for any phenomenon R, there exists a V that causes it. You see that? So the pair of the universal quantifier and the existential quantifier inside of it. In other words, for all phenomenon, there exists a phenomenon that causes it. All right. In other words, every phenomenon has a sufficient reason to exist, you see. This means that the question why is always meaningful. And one of the fundamental questions of science, as I have said, is to answer the question why. Even if we never find the answer, axiom A1 says the answer exists. This says whatever the phenomenon, whatever R, and put any R in there you want, then there exists something, V, which causes it. So, consider phenomenon M. Axiom A1 says that M is caused by something. And suppose, okay, so we put M in here by UI, and then we get there exists a V, such as V causes M. Then we do EI, and we get, let's say we use K. So suppose M is caused by K. So the question is, why M? And the answer is, because K. That's what this axiom says. Okay? Now why is it justified? Now we have talked about absolute phenomenon. There are two alternative interpretations of absolute phenomenon as either self-caused or uncaused. So in these videos we're doing version 1 of G theory, where we interpret absolute phenomena as self-caused. And in version 2, which is the next step on the journey after you've watched these videos, we interpret, as I told you, absolute phenomena can either be self-caused or uncaused. And importantly, in version 2 we do not use axiom 1. We use a different approach. So our interpretation of, in version 1 of absolute phenomenon as being self-caused actually makes axiom 1 true. In other words, so if you have a relative phenomenon, it's caused by some different phenomenon. That's why it's a relative phenomenon. And any other phenomenon is an absolute phenomenon, which we're interpreting as self-caused, which means it causes itself. In other words, every phenomenon has a cause. But let's look at this in the context of science. Axiom 1, if you deny axiom 1, it undermines scientific scrutiny. This is very important in science. Scientific scrutiny is based on asking the question, why? Why do apples fall from the tree? Why do planets sometimes go retrograde? What does that mean? Well, you know, planets move through the sky. They move amongst the stars. They move in a particular set of 12 constellations, which are called zodiac signs. And if Mars is moving along, it's moving along from Cancer into Leo and then into Virgo, and then at some point, all of a sudden, it switches directions and starts going backwards. And then it goes forward again. It really happens. Why does that happen? Very interesting question, very important question. To deny axiom A1 is to affirm the existence of some phenomenon, let's call it H, that has no cause. In other words, H is uncaused. Nothing causes H. And this means the question, why H, has no answer. Why H? Because. Well, that's not a good answer. Well, because why? Well, just because. You know, when I was a little kid, about 4 years old, I had some little kids next door, a couple of girls, and I played with them sometimes. And I remember, I don't know what they said, but I asked the question, "Well, why?" And she said, "Because." And I was not happy with that, and I said, "Well, because why?" And she said, "Just because." You know, that doesn't work for me. This puts H beyond the reach of scrutiny. The thing that has no cause, it puts it beyond the reach of scientific scrutiny. It declares that there are some questions that science will never answer. I don't like that. I like science to find answers. I like to know they exist, that we just have to keep looking. Deny axiom 1 defies the history of science. For example, what causes a particular atom of an unstable isotope to radioactively decay at a particular time? Now, what does that mean? Okay, let's talk about uranium for a minute. That's an element, and one isotope of uranium is uranium-238. It has a particular, the total number of 92 protons, and then the rest add up to 238 in neutrons. And so, actually, I think earlier in this video I said that aluminum had 13 neutrons. It actually normally has 14. Sorry about that. Anyway, so the uranium-238 atom is not stable. If you have a pound of uranium-238, then after a while, those atoms will decay. And after a particular period of time, it's a long time, but a particular period of time, half of them will have decayed. And that same period of time, another half will decay. Well, the question I want to know, well, what about this uranium-238? What about this atom right here, this one right here? When is it going to decay? At some point, it's going to go poof and throw off an alpha particle and become something else. Now, when will that happen? This question has never been answered by science. Does that mean it will never be answered? You know, Einstein famously said God does not play dice with the world. But quantum mechanics, which is the best understanding we have of these phenomenon, basically says that there's a dice throw involved. Einstein didn't like that, and so I think that maybe there will be an answer to this question eventually. The entire history of science demonstrates ever-increasing progress, looking deeper and deeper into causation, answering chains of why questions. Why does this decay at a particular time? And perhaps a century from now, scientists will have a much deeper understanding of radioactive decay and of quantum mechanics, including why this particular a particular atom decays at a particular time, and maybe we could actually predict it at that time. I don't know. In fact, the history of atomic theory supports axiom A1. In the 1700s, much was known about chemical reactions, and much was learned during that time. That was Lavoisier's time. But most people thought matter was continuous, meaning it didn't have any atoms. But then in the 1800s, the existence of atoms and molecules was confirmed, but their tiny size could not be measured. No one knew their size. They just knew they were very small. And then in the early 1900s, Avogadro's number was actually measured at 6.02 times 10 to the 23rd. And that enabled us to know how small the atoms were, how many there are. Also, subatomic particles were discovered that are inside the atom, like protons and neutrons. And atomic power was realized. This is a big deal. And then in the late 1900s, we could actually see individual atoms now with super microscopes. Oh, there's one. Oh, there's one. There's one. And today, with nanotechnology companies actually manufacture products by building them up with individual atoms. Like, we'll put one here and one here. It's a manufacturing process, like building a house from individual bricks. Incredible. So how can anyone be so certain that we will never know what causes a particular atom of an unstable isotope like uranium-238 to decay at a particular time? All right, so now let's move on to axiom A2, which says that causation can happen in a chain. Here it is. This is called the transitivity axiom. And what it says, like I said, causation can happen in a chain. And here's how it works. I'll show you, we'll talk about the logic in just a second. Okay? If it says if I have three phenomenon, R, S, and T, it says that if R causes S, and S causes T, as you can see in the diagram, okay, then R causes T. In other words, there's a chain happening. And let's look at the logic up here. We have three universal quantifiers out here, for all R, for all S, for all T. And now inside these big parentheses, we've got some square brackets. And inside the square brackets, there's a conjunction, an and, right there. And what it says is, it says R causes S and S causes T. Well, that's what's shown in the diagram with the solid arrows. In other words, that, if we know R causes S and S causes T, that in square brackets implies, in other words, if all of that, that implies that R causes T. You see? That's how it's stated in logic, exactly what I've just been saying. So this means that R causes T by way of causing S. Now a classical example, it's a loose example, of this is a domino chain. I have a bunch of dominoes lined up. Now the fall of the first domino causes the fall of the next domino, which causes the next one all the way to the last domino. All right? It also means that why questions can chain backwards to reach a deeper reason. Okay, well, why T? Okay, looking at this diagram. Why T? Well, because S. See, S causes T. But really, I want to really know why T. Because R. R is the deeper reason. R, which causes S, which causes T. See? Now, why is axiom A2 justified? Well, to deny that axiom A2 is to affirm the existence of three phenomena, let's call them H, I, and J, where H causes I and I causes J, but H doesn't cause I. But how can this be? H is a sufficient cause for I, including everything that I does, such as causing J. Therefore, H is a sufficient cause for J. To deny axiom A2 is to deny the general existence of causal change. For chains, for dominoes in a sequence, it's to say that the fall of the first domino somehow does not cause the fall of the last domino. I think that's absurd. So now let's move on to axiom A3, the two-way causation, the non-circularity. This is called the non-circularity axiom. I'll explain the logic here in a minute. What this does, it prohibits two-way causation loops. So I have two phenomena, R and S, shown right here. It says, okay, R causes S and S causes R. No. That's prohibited. Unless R and S are the same thing. Okay, well, if they're the same thing, then that's what just causes itself. So what does this say? It says that if R causes S and S causes R, then they cannot be different. They have to be one and the same. They have to be equal. So now let's look at the logic up here. I have two universal quantifiers. I have for all R, for all S. And then I have a conditional in here. But on the left side of the conditional, there's square brackets, and inside there it says, R causes S, so that's going that direction in our diagram, and S causes R, going back the other way in our diagram. All of that's on the left side of the conditional. So if all of that, if R causes S and S causes R, then what? R and S are equal. They have to be equal. In other words, this can only happen if R and S are equal. All right? And this does not prohibit self-causation. It's okay to put, if you want to put in the same thing for both R and S, that's fine. Then it's okay if they're equal. And now when you put this together with the transitivity axiom, it can prove that longer loops are also prohibited. So going around several phenomena, well, I guess this way, going around several phenomena and coming back to the same one again, no, that's not permitted. All right. Now, axiom A3 is justified. You know, to deny axiom A3 is to affirm the validity of circular reasoning in answering a why question. Why R? Because S. Why S? Because of R. This is absurd. It's a logical fallacy. You know, circular reasoning creates an infinite loop, and it never lands on any firm answer. It fails to answer the question. It fails to tell us the cause of R, and it fails to tell the cause of S. We don't get either one of the answers. In fact, it undermines the entire notion of causation and makes it meaningless. But what about the chicken and the egg? You know, well, the chicken causes the egg and the egg causes the chicken. Does the chicken cause the egg and the egg cause it? Is this an exception to axiom A3? Does this undermine our axiom A3, the chicken and the egg? Well, no. The chicken and the egg do not violate axiom A3. Let's look at actual, real, physical chickens and eggs. Okay, egg 1 causes chicken 1. And then that chicken lays an egg. So that chicken 1, but it doesn't lay the egg that it hatched from. It lays a new egg. It lays egg 2. And then egg 2 hatches into chicken 2. So it's not going around in a circle. It goes forward. But look at the abstract principle. The abstract principle of the chicken and the egg. Okay, well, chicken causes egg, egg causes chicken. Well, that's not quite true, you see. The abstraction of the egg. If I talk about an egg in an abstract sense, it never hatches into a chicken. And the abstract idea of a chicken, it never lays a real egg. Instead, the abstraction is of a single subspecies called Gallus domesticus, which has 2 phases. This is a life form with 2 phases. It has the egg form and it has the adult form. And so here's what's happening causation-wise. You see, the species, or subspecies, Gallus domesticus, on the right side here, that's a phenomenon which has 2 parts to it. It has the egg, the abstract egg, and the abstract chicken. There are 2 phases of this kind of animal. And what has caused that? Well, I don't know what, but I've put some things here, some ancestral species, the evolutionary process. I put some question marks. I'm not sure what brought chickens into existence. But they came into existence presumably together, the chicken and the egg together. All right, so it doesn't violate axiom A3. Okay, so that's it. That takes care of video 6. We've got this all cyan now. Now, where are we going to use this? Well, we're going to use this immediately in video 7. We're going to use the undefined terms and one of the definitions. And we're also going to use it in our in video 8 when we do our formal rigorous proof. And then, so that's it. So I hope to see you in the next video, which is video 7. Thank you for watching. And I'm Mark Lawrence Donald Emerson.